This is the last class of this. I guess you probably all knew you were part of an experiment. It wasn't a big deal about it being experimental, but this math course came into being about 4 months ago. It's something I've thought about for quite a while, about how one would teach math in our time. I certainly did not like the way math was taught to me, and I think it's still a big problem about how to teach math. So this was my go at this. How would I do it if somebody allowed me to do it? And so this was the first time out. And like everything that you do the first time around, it has bugs. And I'm quite aware of some of the things that worked and some of the things that didn't work so well and some of the problems. And so I want to first of all thank you all for coming and hanging in there and sticking with it. And I want to apologize for the things that left you at bay, left you like, I don't know what's going on here. And I want to speak to that because I have my way of teaching is not to build it like a building, that you get all the little bricks in place and then you can build the next layer and the next layer and the next layer. I'm inspired by the way we learn as children. We all came in, nobody said, you first of all have to learn this and then you learn that. You learned language just by being in the presence of people who were speaking. And you got it for free. It's part of your endowment as a human being. You didn't have to get trained to speak and hear people speaking. It just naturally happens. It's part of being human. But you did not come into the world knowing how to write or how to read. That had to take work. One of the things that happens when you come into the world also is you're hearing your parents speak, your siblings speak, people speaking, and then pretty soon you're speaking and you're hearing. You can look at the natural world, all the things in the natural world, in particular the sky. And I don't know if you can think back much about looking at the sky, or first of all knowing that there are stars. So the first thing we learn is, fine, yeah, there's stars. Look at that, there's stars. And then at some point you see, well, there's some special stars that are always kind of specially bright. And some of the stars have shapes. And maybe you see it, and maybe somebody points it out. Probably, usually it's pointed out to you that there's a dipper. And in fact, there are two dippers. And then you might learn as you go along, growing, that the dipper's tail will point to the pole star, and the pole star, if you look at all the stars, they go around every night. Well, you can't see that because you have to do something a little more explicit to see it. If you take a camera and expose it after dark and leave it exposed all night and then close it before the sun comes up, you'll see all the stars going around in circles. And then maybe you see one of these great constellations like Orion that in the wintertime is big and bright and high, and then in the summertime he fades away. The point I'm trying to make is you got the whole sky right from the get-go. And then you started to try to make sense of it. That's the way I'm teaching. In many ways, I'm giving you the big story right from the get-go. And it's going to throw you a bit. And some of its parts are going to be missing, and you don't know how they work. But that's the strategy I'm exploring here and would like to use. And of course, it has its problems, and it's because there are some things that you just don't get, because I'm throwing the whole thing at you. But as you go on, things start to make a little more sense, hopefully, and pieces are falling into place, and the picture starts to fill out, and hopefully you get it. So that's one thing I wanted to say. That's why the style of teaching here is a little different. The other thing that I wanted to point out is you got language. Everybody speaks, just about. Literacy worldwide is only 7 out of 10 people. Only 7 out of 10 people in the whole world actually can read and write. So you obviously, being in the developed world, many more, it's a much higher percentage of the population that can read and write. But what I'd like to point out is that you had your natural language that you got for free. Reading and writing required work and effort and education. I would like to suggest there's another level that we're emerging into right now. We've been emerging into it for several hundred years. And that is a mathematical and scientific literacy level. And most of the world is completely illiterate in that. The number of people who are mathematically and scientifically literate worldwide is probably between 1 out of 10,000 or 20,000. So if you have 20,000 people in the world, only one of them is capable of
What are you defining as literate?
That you can write mathematics and read mathematics, that you can write physics and read physics, you can write biology and read biology, or some combination of them. That's what it means. And even in a highly developed country like the US, for example, it's really only like 1 in 100, or maybe 1 in 500. So most people are mathematically and scientifically illiterate, except for popular science. And perhaps you've noticed that in terms of the growth industries, so to speak, if we call them industries, in America and worldwide, they are the computer science industries. They are the Googles and the Apples, and these are highly mathematical and physics oriented, and hardly anybody can do it. I don't know quite what to make of that, but that is kind of the situation. One way of thinking about it is, it's like literacy was 500 years ago, where most people were not literate. If you were a monk in a monastery or worked in the court of the king, you could be literate. Otherwise, you were not literate. I don't have the answers to any of this, but I just think it's worth observing that if you can speak and write mathematics and science, you are in a very small set of the American population, or even the worldwide population for sure. I, of course, would like everybody to be literate mathematically and scientifically. I think it's part of understanding and appreciating and celebrating and knowing the universe in which you exist. So that's the situation. You're maybe part of the leading edge of something that's happening. I hope you're the leading edge of it. And now we come to the last lecture in this series. And I confess, and I apologize, that this lecture is probably going to be as difficult and as full of stuff that is getting thrown at you as any of them have been. And I apologize, but this is the way I wanted to do it, and maybe I'll correct course. I will correct course. It's not going to be so much thrown at you at one time. So if I do this again, obviously we're going to learn from this experience how to pace things what needs to be prepared a little better and so on. So it won't be quite so rough. But thank you all, because you came into the first blast of this and had to suffer all of its limitations. So the last thing I wanted to do is what I think is an enormously beautiful connection between the circle and the hyperboloid. They happen to have those names, but they're basically variations of the sphere. And the thing that is so remarkable about it is these simple mathematical shapes are right in the foundation of space and time, right built into the universe. So just to remind you where we were, we spent a fair amount of time on the circle, and I asked you to get yourself as best you could literate in the circle so that you knew what's going on with the circle. And there's a one-slide summary of the circle. It's Euclidean. What does that Euclidean mean? It means y squared plus x squared equals r squared, or any y-x pair. Say you have another x prime and a y prime. If they're lying on that circle, then they have to also equal r squared. And the x and the y that you get for any angle that you pick going around the circle are related to the radius by cosine and sine. And I didn't talk about it specifically, but there's something called the tangent, which is just the ratio of y to x. All right, so what we're now going to go on, that's just space. There's no motion, there's no time, just the static structure of space. A rotation in what we just saw is basically changing your direction in space. But now we're going to bring time into the picture. And when you bring time into the picture, you have to talk about frame. What is a frame? Well, it's a coordinate system for motion, and since we have time, the frames can move. And different frames, when they move, experience different effects. So a frame, first of all, starts with just the idea of a timeline. I think you're all familiar with timelines. You can have the timeline of your life, where you were born, when you started school, et cetera, timeline. Those are very familiar. But what we're talking about is the physical world in which things are not only just moving in time, they have places in space. They have a location. They have a place where they are. So this timeline, when we bring space into the picture, so here's the timeline. Maybe there's a point on here, we call it t equals 0, for example. We add space to the description so that things can now exist both in space and time. So every point in this plane is a space-time event. That is, it has a certain time that it happened, and it happened in a certain place. And the lines themselves have a very important significance. A constant time, where time is, this time is 0, say this time is 1, these timelines are all lines of simultaneous events in space. In other words, every x on this timeline happens at the same time. The events are simultaneous. That wouldn't be true of some line on an angle. The other thing is that, back to the timeline here, say this timeline goes through the point x equals 0, right here. There aren't any other x points involved. This timeline only intersects one x point, so all the points have the same x value, And we call those, what this is a line of rest. Nothing's moving on that line. They all have the same x value. So now if we have a line that, this is a line of simultaneity, this is a line of rest, anything in between is a body in motion. And so these slanting lines, this is a body in motion going backwards in this reference frame, this is going forwards. The velocity is just the ratio of the x-coordinate to the time coordinate. And the more this slopes this way, the faster you go, until finally you're at rest. Here you are at rest. Here you're moving infinitely fast. Here you're moving at some velocity. Here you're moving at some velocity going backwards. All in this particular frame of reference. So I want you to think about the idea of a very interesting idea in space-time. It's called the world line. Not just a timeline, because it's got space mixed up with it. So a world line is a path through space-time. And one of the most important kinds of world lines are light rays. These are lines that lie that move, the particles move at the speed of light. So they're moving, and so they are lying at an angle. They're not at rest. And they have a certain maximum speed, the speed of light. And the equations of those lines are t plus x equals 0 and t minus x equals 0. We've talked about those before. But let's look more generally. I've shown that because it's not possible for any particle to travel faster than the speed of light, I've sort of shown this as what's called the light cone, because this region out here, which I've labeled inaccessible, is inaccessible. You'd have to go faster than the speed of light to be in this region. So this is the past, this is the present moment right now in this reference frame, and this is the future. So a particle can begin moving from the past, come into the present, and continue on into the future. And it always stays inside the light cone of this point. Every point in space-time has a light cone. Another point over here has its own light cone and its own future, past and future. So this is perhaps one of the surprising things about finite speed of light, is that there are regions of space-time that we can't know anything about until later, maybe, when the signal finally might get to us, and then we have to kind of infer what happened, because we couldn't actually be right there at the event.
Reverse engineer it.
Sort of reverse engineer it, exactly. Yeah. And that's an essential part of cosmology. That's part of the toolkit, is how to reverse engineer and reveal what happened in inaccessible regions of space-time using, as you say, reverse engineering. So world lines of light are never at rest, and in this diagram, the speed of light is just one unit, so that's why they're at 45-degree angles. And light speed, in case you want to be reminded again, is 186,000 miles per second. And I should say, it's not just light. There are other particles that are massless and therefore move at the speed of light. But any particle that has mass, like atoms and molecules and so on, they have to move at a speed less than the speed of light.
Wait, light doesn't have any mass?
It doesn't have any mass.
I thought I had like a
It has energy. Has energy. And this could be a little surprising, but it has energy, and you might know that Einstein showed that energy and mass were equivalent. E equals mc squared. Did you ever see that or hear of that? So there is no rest mass for a photon, but it can have energy. Okay, now we're going to leave this world of Euclidean space and start to enter the hyperbolic space-time. So in Euclidean space we had two space coordinates, and one of them was x, the other was y. We're dismissing the y coordinate. We're saying go away, we're only going to have a one-dimensional world here. It's only got one space dimension, and we're going to replace the role that the y coordinate was playing. We're going to replace it with time, and I've changed the name. I'm labeling it t now because it's time. And the amazing thing that still I find somewhat stunning is that the equation that you have describing space-time is just like the Euclidean equation for space, except the sign is changed on the space component. But they have to sum up to a constant. And this little symbol here, it's the Greek letter tau, is like the radius of the circle. It's playing the role in space-time what the radius was playing in space. And because there's a minus sign here, this right-hand term can either be positive or negative. So when it's positive, we have these hyperbolas here, and when it's negative, we have these hyperbolas. So that's the story, and I've put the circle, the Euclidean circle, into the picture here just so you can see it. It's not part of this equation. It's just there to compare with the Euclidean space. So now we can have rotations in space-time just like we have rotations in Euclidean space. So in Euclidean space, the rotation of a space coordinate into a space coordinate changes the direction. So if I have the x coordinate and I rotate it into the y coordinate, what I'm doing is changing my direction, changing the direction I'm going, if we're in Euclidean space, purely spatial. But in space-time, really interestingly enough, since one of the coordinates is time and the other is space, a hyperbolic rotation is a rotation of space into time. And what that does is change the velocity. So if you had no velocity when you started out from a line of rest, and you rotated it in space-time, you would now be giving it velocity. It's sometimes called boosting, and sometimes the rotation in space-time is called a boost. So rotations are common to both. The actual mathematics of the rotation is a little different because of that minus sign. You'll see that there's an enormous correspondence between all of Euclidean mathematics and hyperbolic mathematics, with little shifts, little changes because of that minus sign. So now, here's the world line. Here's the world line of a body at rest, zero velocity in this reference frame. Here's the world line of a body rotated into motion. It's got a velocity that's equal to x over t. I want to emphasize that this is for this reference frame. If I have another reference frame that's in motion, I can actually rotate this world line so it's back at rest. So, for example, if Gabby is moving along at a certain velocity, then this might be her path. So she's driving her car at this velocity, and maybe Marin comes along and she's got a car and she can go a little faster, and maybe Gabby was going first, but she can catch her. She can drive faster and eventually get up with her. Even if she leaves later and drives faster, she will catch her at this point. And then if she just goes parallel with her, looking at each other in the car, waving, they're in a rest frame. So by being in the same frame, even though they're both moving relative to the ground, they're both in motion relative to the ground frame, they are at rest with respect to each other. So you can always bring a body to rest. If you have a rocket ship with enough fuel and power, you can chase after something and eventually catch it and then move with it. If there's no restriction on how much energy you have. You can't do that with a light wave, because light, magically enough, is 186,000 miles per second no matter what speed you're moving at. So if Gabby was driving in her car at going 100,000 miles an hour, and she might think she's going a good bit of the light speed, and if there was a light ray going behind her, she could slowly catch up to it. Actually, Einstein actually did this thought experiment when he was a young man. He imagined that he was running after a light wave. So here's a light wave, turn on a flashlight, there goes the light wave out, and it's actually got sines and cosines in it. It's oscillating, light waves moving along. And Einstein said, well, why can't I go as fast as the light wave, and pretty soon I'm not seeing the light wave going like that, I'm seeing the light wave just do this. I've stopped it. And he said, that's impossible. Why did he say it's impossible? The reason is one of these things that's going to be beyond you again, because he also knew the equations of electrodynamics. The equations of electrodynamics say light speed has to be constant. You can't change it. You can't bring the light to rest. But he puzzled about it. He said, can this really be true? This is before his very famous paper of 1906, when he basically taught the world that time is relative and that light, the speed of light is the same no matter whether you're going 186,000 miles an hour or standing still. But everything else would change. So here we are now with our hyperbolas. And how do they fit into this story? Well, here's again a world line. And it goes to this hyperbola. If I rotate it back to where it's at rest, I have to stay on the hyperbola, just as when you rotated a line in Euclidean space on the circle, you had to stay on the circle. You couldn't just go any place. You had to move the point on the circle. Point has to move on the circle. This point, as I change speed by changing velocity, it has to stay on that hyperbola. Okay, so that's good. And if I boost boost this this point into the opposite direction, so that then you go in the opposite direction. That's perfectly natural. And this is all accomplished by changing velocity. Bring the velocity back to 0 in this reference frame, and you are back here at rest in this reference frame. Now I've marked these two different reference frames with these little primes. So when we boosted the reference frame out of the xt frame, that's the original one we started from, we boosted it. When you plot it in the Euclidean plane, it looks kind of screwy. Well, it's not screwy at all, it's a hyperboloid. But this is a line of rest in the boosted frame. So that this is, if Gabby's driving 100 miles an hour in her car and going in that direction, and this is her line, she's at rest with her car. She's not going 100 miles an hour with respect to her car. She's going 100 miles an hour with respect to the Earth. So in the reference frame that t prime is the time of, things are at rest. But in the reference frame in which the time is measured by t, she's in motion. And the same way for the x and the x prime. The x prime is the line of simultaneity. This is the line in which everything is simultaneous. This rotation of the x into the x prime, this rotation of the space coordinate was bizarre to the people in the 1900s. Because everybody knew about this rotation. Everybody was cool with that. That makes sense. You go in motion, and you're going to be in motion with respect to the Earth, say, but inside your car as you're driving along, you are at rest with respect to your car. So everybody's fine with that. But that the time in which you are measuring in your car as you're driving along compared to the time that somebody is measuring standing on the Earth watching you zip by, that those times are not the same. That was hard to believe. But that's exactly what happens when you obey that equation. And there was good reason to think that the idea that the space wouldn't change, that bothers people, because it says, why is this so ugly? Why hasn't this got a beautiful rotation to it like Euclidean rotation? Instead, it's got this kind of half-baked rule of, yes, you can rotate the trajectory, you can rotate the path into space-time, that makes sense, but that you change the simultaneity between events, that clocks are running differently in different reference frames, that's hard to buy. But if you say, well, we're not going to buy that, we're going to keep it, we're going to make time the same everywhere, all over the universe, time runs at a certain rate and that's it, you get this ugly mathematics. And there's a way in which a lot of imagination about how the physical world works was motivated by beauty, motivated by it had to be beautiful. That's what motivated Kepler when he came up with his theories about the ellipses as the shape of the orbits of the planets. Because the previous theories were like tables. They just had numbers, observations, and a way of predicting that was hugely complicated, very ugly. And Kepler believed that it had to be beautiful. And the ellipse actually hits it pretty well. For most of the planets, it's pretty close. So this change of simultaneity, that things are not simultaneous everywhere, depends on how you're moving, was kind of a shocker. And this, when you're in the moving frame, which is, here's where your x-coordinate is now, it's no longer simultaneous with this x-coordinate. And that's life. That is the way it is. But it's beautiful. Okay, oh, let me say something here. When we had our Euclidean circle, we had x equals r cosine theta. Now, I've used tau as this symbol for the so-called radius in space-time. Here's the rule. So suppose I rotate to this angle theta, give a boost. What's going to be my x and y and t coordinates? Well, here they are. X is a certain constant, t, so tau, times cosh. What is cosh? I'll tell you in just a second. Just think, must be close to cosine. Kind of sounds like it, kind of looks like it. It is close to cosine. So the rule in hyperbolic geometry is that x is equal to cosh theta t, which was we pushed the y-coordinate out and replaced it with time. We needed to have that space so we could write time. That's sinh, which is the hyperbolic cosine, and tangent is just the ratio of the two, just like in Euclidean space. So here's where you come in, Adrian.
Me.
Yes. So what are sinh and cosh? What is that all about? Well, it comes out of the hyperbolic geometry. And remember, I said these two geometries, Euclidean and hyperbolic, are intimately related except for little small effects. Now, I don't mean those are trivial effects. Making a change, like changing that sign from a plus to the minus in the x squared plus y squared versus x squared minus t squared, blew the circle to pieces, blew it into 4 parts. So it's not trivial, but it was simple. It was really simple. So if you know what sine and cosine are, you know what sinh and cosh are. So Adrian, what do you think? So what is this I?
I?
Yeah.
Negative square root of negative 1.
That's right. But I also like to think of it as an operator that rotates something by 90 degrees, as you recall. Mm-hmm. So, but both are perfectly good ways of thinking about it. We need to use both. We need to have both ways of thinking. So if you want to know what sinh is, what is it? It's the sine of an imaginary angle, because theta is a real number. So this is a pure imaginary angle, and you say, well, that's crazy. What is that? Well, what it does is it's what's accounting for this blow up of the circle and the fact that you don't go round and round. On the circle, theta goes round and round. In hyperbolic geometry, it can go as far as the light ray, and that's it, or back to this light ray. That's as far as it goes. So the sinh and the cosh don't go round and round. And the way you stop them from going round and round is by taking the sign of an imaginary number. Now, you're not going to understand this completely, but just appreciate that there's something that's not that complicated here. The sinh is essentially the sign with, now there's also a minus I that's sticking on here. The cosh is a little easier. It's just the cosine of the imaginary angle. It doesn't have any I. And the sinh and the cosh and the sine and the cosine, the sine of a real number, not the sine of theta, not I theta, sine and cosine are real, sinh and cosh are real, but you can produce from the sine, by using an imaginary angle, the sinh and cosh. Okay, so I just threw that at you. And hopefully some of you will see it again. And it's a little bit, maybe like the first time somebody pointed out Orion and you saw that he had a belt, but you didn't know much else about it. This is the first go at this probably. Have any of you seen this before? Okay, so this is like the first time. First time. Now, this is what I had hoped to achieve in this lecture, was an understanding of this picture. And in some ways I feel that it wasn't successful. It wasn't successful in the sense that you had everything you needed to take it in. But I think it is successful as if I were pointing out the sky to you and trying to, maybe for the first time, I'm trying to show you how the dipper, the tail of the dipper points to the pole star. Something like that, maybe. So here are two pictures. Here's what we did for a couple of lectures before this one. This is the story of the circle. This is the circle story. And it's Euclidean space. It's got the familiar plus sign, and it's got the familiar trigonometric relationships. R is cosine theta, R sine theta, tangent theta is y over x. That's the circle story. And over here is the story of space-time. Well, you could also just say, if you are very much a partisan of pure mathematics and don't want to see it related to physics, you could just say, well, this is just hyperbolic. This is hyperbolic space. There's the sign that's changed. Any pair of coordinates that are going to satisfy this space-time have to be moving on hyperbolas, just like these had to move on circles. And here are the relationships between the x coordinates of the points and the t coordinates. X, t. These are sinh and cosh. And these are cosine and sine. So I think this is a kind of, if there was a holy book of science, this would be one of the pages in the holy book. So here we are. You can see how the rotations behave. Oops. And here is, all of that was for, we sent the y coordinate away because we needed to make room for the time coordinate. But I wanted to show you that because we can visualize 3 dimensions in the plane by projections, I thought I'd show you that if we brought the y coordinate back into the picture so that we had x, y, and t, in the real situation we also have z, so it's 4-dimensional, but you can't see easily unless you have trained yourself to see in 4 dimensions. But you can visualize 3 dimensions in the plane. So since we have that capacity, I thought I'd bring back the y. And I took this slide from another piece of work of mine, and so some of the symbols look a little funny. But this essentially is the light cone again. Sitting inside the light cone are the hyperboloids, and these hyperboloids are 2-dimensional. They're not just 1-dimensional hyperboloids. And you see that the hyperboloids are shaped like hyperbolas, but if you go around this way, they're circles. So these hyperboloids are built out of circles, along a skeleton that is essentially hyperboloid. So you see how the two things come together. And again, outside the light cone, it's inaccessible. There's a past and a future. Okay. Now, we talked about how this hyperbolic geometry changes what happens when you rotate into motion, and that simultaneity is lost. So, first of all, I'm going to talk about, maybe we'll talk about that first. What happens is, let's get oriented first here. I'm going to tell you the facts, and then we're going to look at how they play out. So the lengths of objects are shorter in the frame in which they are observed to be moving. So if this ruler is moving and you're stationary, you will see that it's shorter than I will see because I'm moving with it. So I measure this ruler, I get a certain number. You measure it, maybe by bouncing light signals off. I mean, you can't stop it. And you get a shorter number.
I get like lines in the interstate when you're driving along. They seem like they're really short, but if you like stack your car, they're like a car and a half long.
That's not quite the same effect. It's not, no, it's not quite, no, because you'd have to be going at, driving at about half the speed of light to see this.
All right.
This isn't going to be noticeable until you're moving close to the speed of light. So that's one of the first things that happens. And this effect is called Lorentz contraction. It's named after the guy who discovered it. And it's contraction, so that moving spatial objects contract when you're looking at them. Now this can sometimes be confusing because you don't think, well, wait a minute, am I in the frame with the ruler or am I looking at it? So pay attention to this. You're stationary out there. I'm moving with the ruler. I measure this ruler and I get a certain number. You measure it while it's moving, you get a smaller number. If I hand you the ruler and then you measure it while you're holding it, you'll get the same number I got. But if it's moving, you'll get a smaller number. The time situation is like it's slightly reversed. So now you have to imagine that I got a clock. I'm sorry I don't have a clock. Put the ruler away. Imagine I have a clock. Okay. So the clock is running. I'm looking at the time on the clock. And you are looking at the clock too. But the clock's in motion. So I get a certain time. And the time you will measure will be longer. So that the time on this clock, when you measure it, seems to pass slowly. So time passes slowly when you're in motion compared to the time and frame in which the motion is observed. Let me go over that again, because I often get this confused. And I must just be sure I haven't. Let me tell you an example. We have cosmic rays. These are high energy particles that are made in stars and in the sun. And they travel almost at the speed of light. And so they come and they're constantly bombarding the Earth. So people like to measure them and observe them. Now, the lifetime of this, what these are very high energy, unstable particles. And as soon as they spring into existence, they almost immediately want to decay into something else. So their lifetime is very short. Yet they make it all the way to the Earth. Well, how do they do that? They do that by traveling close to the speed of light. So that when we measure their lifetime on the Earth, we get a much, much longer time than their actual lifetime in their own rest frame. So this is the time expansion effect when you are comparing time in your reference frame with time in a moving reference frame. It can be a little mind-boggling and a little confusing to get this all straight, and you kind of have to work with it. I still find myself getting, sometimes I think, well, wait a minute, am I in the reference frame with a moving particle or not? So don't feel badly if you don't get it clearly. So here's what it looks like. So here's a blow-up of the space-time plane, and here's the moving coordinate, x prime, and this is, we're leaving the t out of the picture for the time being. So here is a rod, say. So here I've got the ruler. And this is what it looks like in the stationary frame. But this is the moving frame, and here's the simultaneity line of the moving frame. So all of this measurement has to be done at a fixed time. You can't measure it at one time and compare it at another time. It all has to be at the same time. And this is the simultaneous line. And so this is what you would measure, again, if you were moving at some fraction of the speed of light. If you were observing this line moving at some fraction of the speed of light. This is what the speed, let's try that again. Erase what I just said. This is what you measure moving with in the moving frame. You're measuring this rod, you're sitting on it, it's not moving relative to you, you're measuring it, you measure this length. This is what you measure when you get off and watch it go by. And the motion of the rod is actually going through space-time like so. These are the world lines of the rod streaming up this way. And so the length when you are stationary, moving with the rod, you're moving with it. And then if you jump off and you measure the rod as it flies by, you get different results. And the result that you get as the rod is flying by is shorter. And some of you might be asking a question, well, how do you measure like that? Actually, it's kind of tricky, because you can't stop it. And just the measurement of how you measure the lengths of moving bodies is a kind of interesting thing in itself. So here's the time expansion. That's the other effect. So here's a line of rest. We're at rest here. And then we boost into motion. And this boost has to stay on this hyperbola. And say I boost it to here. Now this particular time is the time in this reference frame. It's the t prime of it. But the time in the fixed frame is this time here. And the simultaneity line in that frame is this simultaneity, not this one. And so this t that you measure in the frame in which you're observing the moving body is expanded. So I'm going to end with the with again the same slide from the Physics and Mathematics Holy Book. These two wonderful images that have great physical significance in the foundations of space-time. They're also beautiful, and they're also conceptually simple, even if the details of the math can seem kind of difficult at times, like figuring out what its hyperbolic tangent is. But conceptually, that a rotation changes direction in Euclidean space and has to stay on a circle, and it can go around the circle as many times as you want. A rotation in space-time or hyperbolic space changes velocity. And you can't go around. You can't even go around once. You can only go in between the two light lines. The other thing is that Einsteinian space-time for free, it's a little bit like you get language for free by just being human. This hyperbolic space gives you light for free. It says, if you change that sign, then the asymptotes of this equation are going to be these two diagonal lines. I think this, I know this bothered Anna when I did it the first time, but suppose we get way out where t and x are really big. So I'm going to go way out here. X is really big, t is really big, but they're not very different from one another, so that they still satisfy this equation. So when they're really big, I can neglect this radius term and just have t minus x and t plus x. And that's what the equations of those two lines are. And you can see the hyperbolae are trying to grow and reach that. They never reach it until they get to infinity. But that's where the light is. And the light separates them up into past and present, future, and inaccessible. That all comes for free. Comes for free just by changing that sign. Well, I think that's the story. You want to turn the lights on? We'll leave the sacred text up on the board here. So, do you have some questions? Last chance.
I'm curious about the origin in Einsteinian space-time and just kind of how to conceptualize of that.
How he did, how it came about historically. Well, that experiment that thought experiment, and actually thought experiments are really important. Einstein, well, first of all, Einstein knew there's a set of equations called the Maxwell equations, which govern electrodynamics. Has anybody heard of the Maxwell equations? Okay, but you're going to become scientifically literate, right? Aren't you? You're going to promise me that, aren't you? Okay, the Maxwell equations are the equations that govern electromagnetic waves, light. And those equations require that the speed of light is constant. The speed of light can't change. It can't have the effect I talked about of Gabby driving off at a certain speed, Marin catching up with her, them driving together and being at rest with respect to each other, even though they're both moving with respect to the ground. You can't do that with light. The Maxwell equations forbid it. So Einstein knew that, but he couldn't figure out how it would relate to motion, because the Maxwell equations are just about light. They don't have any dynamics about moving particles. And he did that thought experiment of saying, well, suppose I was chasing a light wave. You know, it's running away from me. And if I keep running after it, with a sound wave, you can catch it. A sound wave is also an oscillating wave. And you know the Doppler effect, right? When the sound is coming towards you, the frequency rises, and as the sound goes away from you, the frequency falls. So, velocity, motion changes sound. Sound waves change with motion. So you could catch a sound wave and in effect bring it to rest. That's what happens when a plane is about to break the sound barrier and you have a sonic boom. Because the speed of sound is about like 1,000 feet per second. And so if you can go at 1,000 feet per second, you can catch the sound wave. Well, when you catch the sound wave, what happens is they pile up. It's like heading through snow, and the snow all piles up in front of you, and it makes a big boom.
So theoretically, if you were to go at exactly the speed of sound, would it just more and more sound pile up and it would get louder and louder and louder?
It would probably, if you're going just right at the speed of sound, and you could do it, what happens in an aircraft is that there's locally you'll exceed the speed of sound. It's because the flow goes over the body of the aircraft. So the velocity of the air is increasing in some regions and it's decreasing, so it's not uniform. So some parts of the airplane will hit the sound barrier before other parts. So it's a kind of mushy thing. It's kind of fuzzy as you hit it. There were some people who said back in the 1930s that you will never be able to fly faster than the speed of sound. And we know that if you have enough energy, you can power through it, because you have to feed this pile up of waves, and that energy that you're feeding is turned into sound energy. That's the sonic boom. But light, no, you can't catch it. And that's what Einstein concluded in that thought experiment. He could visualize very well as if it was a sound wave, and he's catching up to it, and he's catching up to it, and pretty soon he's got it stopped. It's just oscillating right there. And that's when you'd have the sonic boom if it was sound. And Einstein said, that's not going to be possible. And then he worked out the mathematics for it. And it's still one of the most lovely, simple, clear papers in all of physics. I think physicists should go back and look at some of the classic papers that have beautiful writing style, clear presentation. So much of mathematical and scientific writing is inspired by belief that complexity really shows how solid it is, shows how really incredible it is. And it's really something more like the sign in those two equations, which is so simple. And yet it's pretty rich in how you play it out with the trigonometric functions and then the hyperbolic trig functions. It's got quite a bit of richness to it. Yeah.
I was wondering if you could talk a little bit about two other experiments. One, I know that the time dilation effect has actually been measured.
Yes.
With instrumentation on.
Oh yeah, they've all been measured quite a bit.
And then the other thing I was going to ask, if you could speak a little bit about, is the twin paradox.
Oh yes, thank you for reminding me. I did want to talk about that. Okay, since time goes more slowly in the moving frame, you can imagine that we have a rocket ship, and we have the twins, and one of them gets on the rocket ship and leaves the other one behind. And then this rocket ship takes off, travels around, and gets close to the speed of light, and then comes back after some time. The twin who traveled, if you look at their ages, the twin who traveled will be younger. Now, there is something a little important about that, well, more than a little important, and it's actually a little tricky to explain how that happens. But you can't, there is, all of the things that we've been talking about have had constant velocity. Well, I showed you one picture of a world line that was kind of wiggly. That one had variable velocity. But everything else we talked about is constant velocity. And those are called inertial reference frames. I don't know why they, well, that's due to Newton, but constant velocity is really important. Conclusions that you make in constant velocity are not valid when you have variable velocity, because then you have accelerations, you have forces acting. It's a much more complicated situation. Can't just simply reason this way. So here's the thing. When the twin takes off in the rocket ship, he's got to turn around. How does he turn around? Well, he turns around by deploying rockets or forces to turn around. It takes force to turn around. It takes acceleration to turn around. So the turnaround is not inertial. And so you can't, that makes it impossible to compare one, they're not completely symmetric. So it makes sense. Something's happened to the twin who is younger. He was in a non-inertial reference frame for a while he was turning around. And that's important to notice, that because you think, well, is that all it was just going at a different speed? No, something physically important happened during that turnaround. Is that yeah, thank you. I did want to mention the twin paradox. I'm glad I almost forgot it.
And one other question, which is a big one.
That's okay.
Just black holes and how they factor into this.
Okay. Everything we've talked about here we didn't say how the boost got done. We just said somehow there's a boost and it changed the velocity. It just, whatever it took, we didn't talk about that. But to change the boost requires an acceleration, requires forces. You've got to apply force to change velocity. And what are the sources of force? Well, the major force in the universe is gravity. So gravity is always the force that's in play. Now here I am, I'm pushing on this table. What's going on? I'm pushing with the cells of my body, and the force is created by the hydrocarbons and such that I've eaten, and the blood that nourishes my cells and makes the myosin in my fingers contract and all of that. And this is so all of these are from electromagnetic forces. These are electrical forces. The forces in the body are all electrical forces. The forces in this tabletop pushing against my hand are electrical forces. So in the widespread space of the universe, the forces, aside from the ones that are involved in forming and reshaping elementary particles, it's gravity. So gravity is, as some people like to kind of crudely put it, it always sucks. It's attractive. Gravity is always attractive. Electricity can be repulsive as well as attractive. Particles can attract, particles can repel. Gravity is always pulling, always pulling, always pulling. So when the hydrogen and helium of the early universe formed, any kind of little non-uniformity is going to grow, because what it wants to do is pull together. So the early universe of hydrogen and helium is essentially unstable. It wants to clump, wants to form into clumps. So slowly it will form into clumps, and the clumps will then, because they produce more and more mass, and the amount of attractive force that's pulling in more mass is proportional to that mass. It's like a runaway explosion. So this mass gets more massive, and if it's made of matter, which it is, it can compress the particles. It can compress them all the way down to where you have only neutrons that are left, and it's called the a degenerate star. So the only thing that resists that pressure is a fundamental quantum effect. That's not so important, but gravity is always pulling, always compressing, and can make tremendous forces and pressures that then can ignite nuclear reactions, which then start making starlight. And if it's a massive enough clump of gravitationally attracted matter, the star can actually explode and make a supernova. And all of that came from this collection of gravity pulling matter together, coupled with the physics of particles that are interacting with each other when you compress them. Yes, Matthew?
So you mentioned supernovas. Is there a real difference other than size between a supernova and a hypernova?
I don't know. Can you tell me? I've never heard of hypernovas, but maybe there's some distinction. I don't know. Do you know anything about hypernovas?
Other than it's just related to supernovas.
Well, if you heard the term, it might be in the literature, and it might refer to some distinction people are making about different kinds of supernovas. I mean, maybe they're not all the same.
Or maybe there's a great distinguishable in size. Like maybe
Yeah.
it's much larger.
That's your homework assignment. What's a hypernova? Jack?
I was thinking like supernovas too, because they do, like the star gets like bigger and then just explodes and just releases, and I think it's like radiation basically from like the explosion.
Well, there is lots of stuff that happens when you compress and get nuclei to get close enough where they can start fusing. The byproducts of that explosion are particles, radiation, gamma rays, light rays. There's quite a lot of stuff that comes out, including both radiation and particles.
I guess part of my question
Could you open the door on
around black holes is because of the extreme density, do they distort the way it's currently depicted in this image is sort of nice and linear, at least in terms of the
yes.
coordinate system.
Yes.
Because
Yes.
of that density, that extreme mass.
Absolutely.
That's warped.
This is all without gravity. This is all flat space, what we would call flat space. This is flat hyperbolic space, this is flat Euclidean space, but it's flat. I have a lecture on black holes. If you'd like to learn more about it, you should look at that lecture where I explain all about how the space-time is warped by the presence of mass. And that warpage is what gives all of these effects, and the warpage can be severe enough in the case of black hole that light can't get out. So do look at that lecture on black holes if you're interested. I think you'll find it quite understandable. Probably more understandable than the details of this lecture on sinh and cosh and sine and cosine and such. I do aim that lecture for a little more general audience. Maybe I'll send a link. Or you actually have
You sent it to me way back.
I sent a link to you. Any other questions? I guess this is going to finish our meetings for this. I don't know what will come beyond this, if anything. This was an experiment. This was teaching math in a very different way than it's normally taught, with the approach that throws a lot at you and hoping that maybe Khan Academy can fill in if necessary. So I need to think about it. It's an experiment. I hope you don't mind that you were part of an experiment. We weren't hiding anything from you. I think you knew that this had never been done before, so there it is. So again, thank you. And
Thank you, David.
Yeah, thank you.